And when you're...
Okay, hello everyone. I hope that this is working correctly. We're going to get started in a couple of minutes. I'm just going to give a couple of minutes lag time for people to continue populating the space. I know this is a new experience for everyone, not exactly what we're used to. I guess some of you have gone through this already a few times. I've tuned in but haven't actually produced. So let's just wait another couple of minutes. It's currently 5:45 right now, so we'll just give 1 or 2 minutes for people to get settled, get tuned in before I make the introductions, and we get started with today's seminar. One thing I can tell you now, there will be an announcement shown in the Q&A window. You should see a Q&A window on your computer, so if you do have questions and or comments, please feel free to type them in there. I actually cannot see that until the end, but we have someone moderating that Q&A, and we will get to questions. We'll have plenty of time for questions at the end of Dr. Wissinger's talk. And yeah, so that's pretty much it. So let's give it another minute or two, and then we'll get rolling. Okay, I don't want to delay too much. So I think it's about 5:46 or so. So welcome everyone. Thank you for attending this virtual seminar today, particularly in honor of Petersheim and the Petersheim exhibition this week, all week long at Seton Hall University. Also, you probably all know this, but let me point out that tomorrow is the 50th anniversary of Earth Day. So it's a very big, important day. I'm David LaVisca. I'm with the chemistry department at Seton Hall University. If you don't know me, I am very happy to be part of an excellent department. And we are very, very honored today to welcome Dr. Jane Wissinger from the University of Minnesota. We welcome Jane to talk to us about green chemistry a little bit, curricular development, her research, which is also in the area of green chemistry. Let me give you a bit of background. I've known Jane for a little more than 3 years, or almost 4 years actually, since the summer of 2016, when I was fortunate to attend a week-long green chemistry workshop at the University of Oregon. And Jane was one of the expert presenters there. I spent a whole week with her at that time, and our paths have crossed increasingly frequently since then, which is wonderful. She is an extremely dynamic teacher and scholar. She got her bachelor's degree at Susquehanna University, her master's at the Georgia Institute of Technology, and then her PhD from Northwestern. And she has really been very celebrated. She's a multi-award winner in both teaching and scholarship. You will see from her talk how incredible she is, both as a scholar, but also as a pedagogue, as someone who really guides students and emphasizes connections between chemistry and the broader context of our world, the environment, and so on. So she is an organic chemistry lab director in addition to her many other duties, and she also works with high school teachers. She really does amazing work. So as I said at the very beginning, it is our great honor to have her here. So with that, let me bring on Jane. and her talk. Oops, let's go back 1 second. Go. Let's see if this is going to work. Okay, I think that everything should be up there. So Dr. Wissinger, thank you very much for being here. Welcome, and take it away.
Okay, so is everybody seeing my screen? Is that what you're seeing? Yeah, okay, David, thank you so much for inviting me. I'm really pleased to be here. I'm with you, even though not physically. I do hope to get out to Seton Hall sometime in the not so distant future. As David mentioned, I'm originally from central Pennsylvania. I went to Susquehanna University, a small liberal arts school in the middle of Pennsylvania, and lots of my friends were from New Jersey. And so I have some connections there. So I was looking forward to coming, but in either case, I'm pleased to be here and part of your very impressive program. I've looked at the schedule you guys have all week for the Petershine exposition. I see you had lots of poster sessions today that I'm sorry I had to miss, but again, maybe in the future. So what I'm going to do today is tell you about green chemistry and why it's my passion and why I believe it's our way forward for a sustainable future. All right, if I can get my slides to go. All right, the first thing I need to do is a tradition at the University of Minnesota, and that is we have a strong safety culture. And before every presentation, every group meeting, every big event, we always have what's called a safety moment, where we share a tidbit of information or reminders so that we're all in the chemistry community putting safety as a priority. And so, apropos, what I want to do is show how green chemistry plays a role in promoting safety. So if you look at the hierarchy of controls promoted by the NIOSH, the Institute on Occupation Safety and Health, you can see that, good, I need to move things around here. Let's see, I'm going to put this down. Little box is in my way. Ah! No, I'm going to do this. Sorry, I'm having some technical difficulties on my end. You're mostly seeing David. All right. How can I get out of this? Okay, let's try this. All right, try that. Okay, does this look good? David?
So hang on 1 second. I think everyone is seeing just you now. So just a second. Let me.
Okay.
Oh, you need to reshare your slides again. So go to the share button.
All right. Let's see if I can find the share button.
In
show presenter.
Teams.
Oh dear.
That's okay. In Teams at the bottom, there should be a share button.
The system not going well.
It's okay.
Teams
Mm-hmm.
and share.
There you go.
Okay.
And then you should be able to choose what you're sharing. Here it comes. Okay,
all right.
so hang on there. Okay, so I think that looks good. Michael,
okay.
Are you seeing both Jane and the slides?
So
I am. Yep.
okay.
And now you've just turned on presentation mode. Good job.
Okay,
you're back to you're back to good.
You're back.
I'll say it quietly, I'm a Zoomer, so I'm not used to Teams, but don't tell anybody. Okay,
No
here we are. If we talk about the hierarchy of controls and how we manage risk associated with going into the laboratory and doing experiments, what we can see is the least effective way to reduce risk, if we consider they're a function of hazard and exposure, is really with PPE. That's because PPE can fail administrative controls. As you go up, the most effective way is substitution or eliminating the hazards, and this is where green chemistry comes in. So green chemistry is all about reducing risk through hazard reduction. And so I like to turn the pyramid upside down, where if you're going to go into the laboratory, the first thing you should do is evaluate, can you find a safer substitution, or can we eliminate the hazard that we have instead of trying to dawn on all our PPE equipment. And one place that green chemistry has really made lots of advances is finding better, safer solvents that produce less waste. And so there's lots of publications in this area that we can use, and lots of solvent selection guides to get us in the green here. Okay, let's journey to Minnesota. What I'm going to do today is share with you an overview. I have to share a little bit about Minnesota, where we are, and convince maybe some of you graduate students to come out here for a postdoc, or you undergraduates to come here for graduate school. I'll share with you my passion for green chemistry and why I think it's so important to incorporate in education. I'll tell you my journey of implementations in the organic chemistry curriculum through sustainable polymers, research, etc., about our green chemistry class. And really what I want to end with is how rewarding it has been for me and how green chemistry has spread and really is paying it forward, I feel, in many, many ways. So let's start with Minnesota. If you haven't been there, it's a beautiful campus. I really came to appreciate it after taking my 3 children to different campuses across the United States. It's a land-grant institution. It is the university in Minnesota. It's in the city of Minneapolis. The only thing missing from this picture is the Viking Stadium, which now occupies, I don't know if you can see my cursor, but a space right here. This is our active learning building on the side here. I'll try to use the laser pointer if this is helpful. Here's our active learning building that you'll see the inside of later. What I'm really proud of is, yes, we are R1 institution conducting outstanding research in all areas. And we have a law school and veterinary school and medical school, etc. But teaching is of a high priority, and our education mission is very, very strong. Okay, whoops, missed a slide. Have to go back one, because I brought all these pictures. There we are, Minnesota up here. Here's our mascot, Goldie Gopher. What a cheery fellow, isn't he? Yes, we have snow, but we also have beautiful sunshine in summers. And what I appreciate most about Minnesota and Minneapolis is the fact that it's sunny here a lot. And central Pennsylvania tended to be cloudy a lot of the time. So I love the sun. It can be 5 degrees and a sunny, crisp day, and the snow makes it sparkly, and I just love it. So if you're considering your next adventure, consider Minnesota. Our chemistry department has over 40 faculty and 250 graduate students, and our focus is really on interdisciplinary science. No one can be just an inorganic chemist anymore, or just a physical chemist. We really all have to work together to solve problems. And so you can see our many disciplines here that we have. Okay, organic chemistry, we must think we're a little bit special, but otherwise we have centers of nanotechnology, sustainable nanotechnology, and energy and catalysis and chemical biology. And what I want to highlight, of course, is our interdisciplinary area of environmental and green chemistry. And there's 17 or 18 of our faculty that really associate their research with environmental or green chemistry. We're also one of the first signers of the green chemistry commitment that Seton Hall is part of. And so we're very proud of that initiative that was taken. All right, why green chemistry? Well, for all of you, think about some of the most important chemical products in your life. So if I was standing there and you were all in front of me, I'd say, okay, turn to your neighbor, and what chemical products are you benefiting from today? And what I bet you would say would be, well, plastics are really useful. I love my cell phone. I'm looking at a computer screen. Food and agriculture, cosmetics, personal care, building materials, medicines. These are all really important aspects and contributions that chemistry adds to our lives. If I ask you what chemical products have been shown or suspect to be harmful to humans, some of the same categories show up. Plastic certainly is a large concern with the buildup on land and in the environment. We're finding pharmaceuticals in our water supplies, and this is the concern because pharmaceuticals are designed to be low dose. And so very small quantities can have effect. Is this is this causing a problem or not? What can we do about this? And certainly electronics, all the elements in your smartphone, most of them are endangered. They're not going to be here in 50 years. What are we all going to do? So these are big challenges we need to address, and we need to do it in a sustainable way. None of us is going to not take that antibiotic to get better because it causes too much pollution. How can we design chemicals so that we still have the benefits that they provide, but a minimal impact on the environment and human health? And that is through green chemistry as these challenges. So here's the long, verbose way of describing green chemistry: the design, development, implementation of chemical products and processes that reduce or eliminate the use and generation of hazardous substances. Okay, that's the long elevator speech. The short elevator speech is benign by design. So let's contrast that to the environmental movement that we're familiar with, started with the seminal book by Rachel Carson, where it's like, dang, we are messing up the environment. We have to do something about this, clean it up and regulate. And so that movement was started, but what we realized is, that's not going to solve all our problems. And so green chemistry, started by Anastas and Warner in 1998 with this seminal book, showed how we can how we can address or tackle these problems through prevention. If you prevent it, you're not going to have to clean it up or regulate it. And this is all about sustainability, people, planet, profit through green chemistry. So the how is these 12 principles that are kind of our roadmap or goals that we can attain. Who? It's you guys, all of you students that are being trained as scientists of any kind, or even those not citizens out there. Even if you're never going to take another chemistry class again, you have a role to play here. So why I believe incorporating green and sustainable chemistry is so important is, first of all, it's safe in our chemistry departments. It's going to provide students of all disciplines to be better prepared to tackle or better prepared for careers in industry. There's a whole group of companies called the GC3 that has put out a statement that says, if we have 2 applicants and we have one that is trained in having a mindset and skills of sustainability and green chemistry, those are the skills we're looking for. It's exciting. How are we going to solve these problems? Solving these problems is important, it's impactful, and students, in my experience, want to make a difference. And so I think that we can demonstrate how important it is and how important chemistry's role is in a sustainable future. All right, so let me show you how I have incorporated green chemistry into my role as a professor at the university and instructor at the University of Minnesota. So we have to start with the snowball, of course. So in 2009, all right, I had one token green chemistry experiment, and I wanted to give it a try. And what I found was with that experiment and subsequent experiments, the graduate students and undergraduates were really jazzed about this idea that we can do chemistry in a better way. And so that ignited my research, catalyzed my research program, and we came out with new experiments, and it was really cool for these graduate and undergraduate students participating in my research programs to see hundreds and hundreds of other students doing these experiments that they developed in reducing the waste in our teaching laboratories. I then became involved in the Center for Sustainable Polymers, which I feel is a niche that my group has really participated in and contributed to, in showing how green chemistry can apply to making better plastics. I'll share a little bit about our extension to high school teacher programs, and then it's just opened all sorts of doors for me. Green chemistry is so interdisciplinary. It takes biologists and engineers and physicists and all sorts of people to make these problems, to address these problems. And so I became involved on campus here with the Institute on the Environment, very active in the Green Chemistry Institute. But what has driven this? It's really the students have driven my involvement in green chemistry, which I really appreciate. And there's students from not just the field of chemistry, but other fields too. All right, so organic chemistry laboratory, I'd probably, if I was looking at all you guys, say, raise your hand if you've taken organic chemistry laboratory. And I'll tell you a little bit about ours. It's a one semester class, so combining 2 and 1, 4 credits. So students are in lab like twice a week and a 1 hour lecture with me. So we cover a lot in a semester. I have TAs, of course, helping me teach the hundreds of students at the University of Minnesota. And I've revised this curriculum to include at least 75% experiments that model green experiments. I also involve or collaborate with our faculty by showing off the work that's being done in our department in the area of sustainability. Also, our laboratory was retooled to be inquiry-based, and this is a natural fit with green chemistry because it's not green or not green. There are shades of green. So an experiment that's probably hundreds of years old, extraction of the essential oil of cloves using steam distillation, can be done. You're using water as the solvent. But contrasted with using a liquid CO2, you can use the tube like shown here on the left, pack it with the cloves, put in dry ice, warm it up a little, and you extract the solvent, contrasted to the steam distillation on the right. So the students are asked the question, which procedure is more efficient and greener? And so this involves looking at the purity of the product you get, considering all the different metrics involved and kind of a life cycle analysis. CO2, what energy do we need to keep that cold? Steam distillation, well, that's cool, you use water, but then we need a solvent to extract, etc. So we evaluate and students evaluate all the different green aspects of an experiment like this in my course. And again, as I said, sometimes there's no one right answer. And that's what science is, evaluating different process. So we have experiments that are solventless. Catalyst is a low-hanging fruit in doing reactions in the organic or other types of laboratory experiments. Really passionate about using renewable feedstocks when possible. Solid supported catalyst. Reactions that are tandem in one pot, saving the energy that it would take to isolate intermediates. Looking at metrics, energy efficiency. We have used microwaves when we have a smaller clientele during the summer. And certainly comparing and using less hazard syntheses. It's always a great thing to do is to look at the Green Chemistry Challenge Award winners for inspiration, and students really enjoy looking at those and learning from them and seeing the exciting advances that are made in coming up with better ways to do chemistry. So I'm going to share a few experiments for you. This is one of my favorites and one of our first experiments that we've published. And it takes borneol, a compound found in nature. It's a terpene. And we want to oxidize it, so secondary alcohol, to a ketone. And I'm sure many of you could tell me a reagent that we could use for this. And maybe one of the first you come up with was Chromate reagent, for sure. This is a really good reaction, but problems with chromates. Chromium oxidants are carcinogenic and corrosive, and the waste is harmful to aquatic life and to us. Disposal is expensive and complicated. This is not good chemistry that we were doing 25 years ago in my organic chemistry laboratory curriculum. So 20 years ago, 15 years ago at the time, they said, wow, you can use bleach. Let's use bleach. And bleach, is that green or not? What do you guys think? Is that a green reagent? For one thing, it wasn't reliable. I'd have some sections getting products and other sections not. And so, and the product was usually wet with acetic acid. It does produce the noxious bleach fumes. So I wasn't convinced that's the best way to go. So going to the literature, what we found was a new reagent. And that reagent is something called oxone. It's a triple salt, potassium salt. Here's the peroxy part of it, that's the oxidizing agent. And we modified the literature using a fancy catalyst to using sodium chloride. Couldn't get much more benign than that. You need the sodium chloride too. 0.3, just a titch of it, makes this chemistry go awesome. And we also took the literature and replaced acetonitrile with ethyl acetate and water, so really green solvents. And this reaction just works spectacularly. And of all the experiments out of my labs, it's the one that's been adopted the most because it is a really clean, efficient reaction that produces nearly minimal, almost no waste at all, because the byproducts can be reduced and they're just sodium potassium sulfate, and they can be put down the drain. There's also a really cool proton NMR. You can see this is an expanded spectrum, and we allow our students to really delve into this NMR. It's fun to talk about camphor because it's a compound that is in our daily lives. Especially if you have a cold, Vicks Vapor Rub, or a cough, you can find camphor in this along with other medicinal products. Plus, you can sublime camphor. It's a great sublimation if you want to teach that technique. All right, here's another. It's not my greenest experiment, but it does illustrate two really high atom economy reactions: the aldol condensation and a Diels-Alder reaction. I mean, the Diels-Alder reaction is just the ultimate reaction. There's no byproducts. You can often do it solvent-free. And so we developed a one-pot reaction where the aldol condensation happens first to give this tetraphenylcyclopentadienone, which is cool purple color. We act it with styrene. This is the not so green part. But we wanted to have the possibility of students figuring out what is the product of this reaction, because they can have endo or exo product or decarbonylation. And so students look at the standard characterizations of melting point and IR, would certainly distinguish between 3 and 4. But what we discovered with this experiment is that the product is extremely crystalline, and we were able to get an X-ray crystal structure. And though not commonly taught in the undergraduate laboratory, it's used all the time. Through the X-ray structure, which we give them the link to, students can observe that the endo product is formed. And they can also evaluate bond distances and bond length. So they can actually see what they've seen for a long time in textbooks, that a single bond is this big and a double bond is smaller, and an aromatic conjugated double bond is in between. And so I really feel like it helps students appreciate the impact X-ray crystallography has had overall in science, especially those people in biology enjoy this chemistry. I would point out what's really cool is this carbonyl here, which is an sp2 carbon, sp2 should be 120 degrees, and what we find it's 99. And so really strained molecule, and you see that in the IR in an upfield shift to 1777 for that carbonyl stretch. Okay, I'm talking, promise those of you who aren't chemists, I'm going to back off from some of the chemistry in a little bit here. Here's another experiment based on the yummy smelling vanillin that can be done in 1 or 2 step sequence. We're again using oxone to use an important reaction taught in all teaching labs, the electrophilic aromatic substitution reaction. And so it's a cool crystalline product. Students, don't tell them that they're just doing this now, that you get the 5-iodo vanillin as the product. And they evaluate this by proton NMR and C13. And you can follow that up with the Suzuki reaction. That was all this chemistry was developed by undergraduate researchers in my laboratories. All right, I'm going to shift gears and talk about my work with sustainable polymers. I actually worked at a polymer company out there in Philadelphia for 5 years at a company called Roman Haas, and I vowed I'd never do polymer chemistry, but sustainable polymers, I am all about it. So this is a topic that everybody can relate to, especially when you see and hear about whales washing up on beaches filled with plastic and albatross feeding their young plastic bottle caps and starving to death. And we see it. Everybody right now, I have no doubt, is touching some plastic in some form. It's part of our lives. And there's many benefits, but obviously there are some problems associated with it. For universities and colleges that want ACS accreditation for their programs, including macromolecules was needed, and polymers was really kind of put on the back burner in a lot of curriculums, and the ACS CPT accreditation guidelines brought it to the forefront. And so we wanted to develop experiments, but we wanted them to be green, because of a lot of the polymer experiments, like making nylon, has really nasty waste associated with it. I was involved in a CPT supplement that also promotes polymer chemistry through green chemistry applications. And what we can really do is associate sustainable polymers with societal problems. That's especially important at the high school level. Well, it's important at all levels. And polymers, they are different than the standard white, solid, or clear colorless liquid often found in organic chemistry laboratories. But sustainable polymers can go into a lot of curriculum, and I'll show you some examples. So what I do share with students to grab their interest, tension grabbers, is this report by the World Economic Forum on rethinking the future of plastics. And let's just focus on plastic packaging. Oh, so how many of us use plastic packaging today? Oh, I see all your hands raised in the air, yes. And that single use, which, you know, it lots of keeps us from germs, sanitation, the medical field, etc. It's really important, but it's all lost to the economy. And I bet if I ask you how many of you recycle, we all recycle, but only 14% of plastic packaging is actually recycled, and this is a real challenge. And the Center for Sustainable Polymers is really addressing these recycling concerns so that we can recycle things that we couldn't recycle before. It's some really latest, greatest research out of that center. And this statistic, as a scuba diver, I really resonate with, and I was scuba diving in January, and it's true, there is tons of plastic in the ocean. And if we keep going business as usual, there's going to be more plastic than fish by 2050 in the ocean. And this is a huge concern. So, what innovations can address these problems? Well, here's an experiment that we developed that's translated from a glove box experiment in the Center for Sustainable Polymer Research Labs to the benchtop at the University of Minnesota Teaching Labs. And that is, you can take this lactone, delta-decalactone or dodecalactone, and you can purchase these as a flavor or fragrance from the Sigma Millipore catalog in kilogram quantities. I love these descriptions: creamy coconut peach-like with celery undertones and buttery creamy peach. So these lactones, in the presence of an acid catalyst, we use this green DPP diphenyl phosphate catalyst, will polymerize to this viscous homopolymer, this viscous liquid. And so that's cool. I wanted students to see more than a viscous liquid. So what we did was use the technology of a block polymer. And that is, if you take this molecule, lactide. Now lactide is a really super important molecule. It's derived from corn, and it's being used to make the most successful bioplastic on the market. So everything that says compostable is made from PLA or polylactide. So if you combine the two products, so this is a Triblock over here, the middle purple blocks is the delta-decalactone, dodecalactone polymer, and put this hard, brittle polylactide on the end, you can get a polymer with amazingly cool properties. And so here's some of the polymers that students in my lab created. And here's the experiment on day 2 that they did. They heat the homopolymer and lactide together to get the Triblock polymer. It's a styrofoamy thing. It's really cool that when you melt it, it's called annealing. And then here's Goldie Gopher. Like I said, very cheery fellow. I have a son at Madison, so I always have to tease them about their grumpy badger guy. And you can see he's leaning on a thin film polymer produced through this synthesis. What's also unique is this polymer can be interpreted by proton NMR because all the blocks are very distinct. So you can use integration to see how big the molecule is. That is it a molecule that's, all the other molecules like camphor have molecular weights of 120 kilograms per mole. This molecule is 30 kilograms per mole. So big molecule. All right. Here's another experiment that we recently published called Dying to Degrade. And it addresses, can we make materials from renewable resources that can also degrade in the environment instead of cluttering up, oh, my pointer's gone wild here, cluttering up our beaches. And so this experiment can fit into multiple types of curriculums depending on what your learning outcomes are. So you can teach Le Chatelier's principle and Beer's law plots and UV spectroscopy and polymer structures and properties with this experiment. And learning outcomes can relate to plastics and society, green chemistry, and design for degradation. So let's take a look. So this uses pretty much household chemicals. That is citric acid, glycerol, and a starch. You can use potato or corn, but we like tapioca root starch. It just has the right consistency to come up with different bioplastics, we'll call them. So citric acid, glycerol, citric acid, starch, glycerol, and starch. Gives you 3 different polymeric type materials. The citric acid glycerol is the coolest. It's clear and like hard candy. So you can see they're pretty much different. We've actually modified this to be a little bit better. We add food dye for the purposes of being able to watch each of them degrade. And so Granted, sodium hydroxide is not out there in the environment, but this is what works in a teaching laboratory. And what we've shown is you can either use a standard UV spectrometer, or you can use a cell phone app. That's kind of a really unique way of taking the pixels intensity and being able to graph the degradation by seeing the increase in the dye as the polymer degrades. So this is a really fun experiment that's been incorporated in a variety of different types of classrooms that works really well. All right, so I'll just show you, here's kind of a portfolio of polymer experiments that my undergraduates and graduate students have developed with me to bring the message of, you know, plastics, the concerns, the impact they have on our lives, and ways that scientists are attacking the problems so that we can have the benefits that polymers provide to us in society without the negative impacts. So I've talked about these two. We have an experiment based on polymeric medical sutures, which is really fun. We have an experiment that we haven't published yet. We're about ready to, that talks about using PLA, that polylactide, for oil spill cleanup instead of polystyrene, which pollutes the oceans. Edible water capsules has recently been published in Celebrating Chemists, and Make It and Break It uses starch polymers also. So happy to share any of these with anybody interested. There really, many of them are good for outreach activities also. And we've had good feedback. I would say this isn't our greatest feedback, but I wanted to share with you that students really feel that this is important topics to include in their curriculum and enjoy learning about how more environmentally friendly and sustainable plastics are being innovated, yeah, that's a good word. All right, so the last topic in implementations is kind of not what I expected. I really didn't ever plan to be involved with high school teaching, but I had high school teachers reaching out to me saying, you know, we want to learn about, all right, my animation's a little slow here. We want to learn about green chemistry also. And this came about also because I had quite a few. I often have undergraduates who want to become high school teachers and want to learn how to incorporate green chemistry. I don't know if any of you can think back to your high school education, but a lot of the experiments done, like lead iodide precipitation, is not very green, and the waste produced from high schools can really be a problem with disposal. So undergraduate researchers and partnering with these high school teachers has really been a fruitful venture in that we've trained over 60 high school teachers in Minnesota to how to incorporate green and sustainable chemistry. We're using a lot of materials, our polymer materials and materials from an organization called Beyond Benign. And as I'll show you later, some of these high school students then learn about green chemistry and want to come to the University of Minnesota to learn more. All right, I'll share a little bit about this dedicated green chemistry lecture course. So in 2010, Bill Tolman, our chair, and Professor Hillmeyer, the director of the Green Chemistry Institute, wanted to design a class that was just about green chemistry. What's challenging about this class is there's no perfect textbook. There's some good textbooks out there, but we really wanted it to be very interdisciplinary. And this class has grown. I'm teaching it this semester, and I have 45 students taking the class. A lot of them are chemistry, chemical engineering majors, but there's also food science and bioproducts and biosystems engineering students and material science students that are interested in learning more about green chemistry based on what they had in my organic chemistry laboratory course. We also have a sustainability minor at the University of Minnesota, and a lot of those students are interested in taking the course. It's taught in that circular building I showed you, active learning classrooms. We teach it as a flipped classroom style where there's readings before they come to class. As I said, we have speakers come in and students are mainly in class doing activities. There are some lectures, but an activity would be the posters like you guys are doing today, having students come up with poster presentations on a greener version to do X reaction, for example, or how can you make a dye more sustainable? So here are some of the topics that we covered. This is a lot to put in slides, but I think many of you may be interested in learning about nanotechnology, sustainable nanomaterials. Lots of benefits from nanomaterials, but there's also challenges, for example, cosmetics, where they're worrying about some of the microbeads. Toxicology, a topic that students are really interested in learning more about. We don't do a good job in the field of chemistry and toxicology, so try to incorporate in this class. Using green metrics, talking about endocrine disruptors. Some cool new discoveries using biomass to make chemicals, platform chemicals, or biomass for renewable energy. And then Cargill is a local company that they were the discoverers of that PLA compostable polymers, and we just had one of their directors in talking about lubricants from plant oils, really engaging. We also talk politics and policies, and this can really engage students in the complexities of, profit, a company needing to make profit, but the impact on the environment, etc. So this is our green chemistry class that we're teaching. In that, we also connect to the UN Sustainable Development Goals. If you're not familiar with these, I really encourage you to look it up. It's one of the best websites I've ever seen of conveying information. These goals were developed by the UN, of course. There's 17 of them. Each of these have sub-strategies, and the goal is to address these concerns by 2030. Many companies, if you go on their websites, are tying their work into the UN Sustainable Development Goals. And again, what we want to do is train students to understand, recognize that they're there, and also motivate students that this is an area you can have a huge impact in the world. I know a lot of students come to organic chemistry class and want to be doctors or dentists, but what I try to convince them is that if you want to have an impact, you can also do it through green and sustainable chemistry. And there is huge potential for making a difference. Oops, okay. So I am coming to impact and rewards. I'll just share with you my personal journey again, or experience in teaching green and sustainable chemistry. So what I believe are impacts, and I have some proof, is that you definitely improve safety and reduce waste. So I've created videos for my organic lab class. I even teach students how to wash their glassware, because once a student knows you can clean everything with acetone, the waste jars pile up. But I've been able to almost half, I've kind of stopped doing this because I was happy that we've halved the amount of waste per student in my organic laboratory class. Plus, I have greater peace of mind, for example, getting rid of nitric sulfuric acid experiment and replacing it with that oxone. Inspiring students. I'll tell you a story about this student, Emma Corcoran. She did not like chemistry in high school, but I went into her classroom with Cassie Knudsen, her high school teacher, and we did that medical sutures experiment where we showed the difference between a suture that's degradable and not degradable and how green chemistry fits in. She came to the University of Minnesota, joined my research, took my organic chemistry class, joined my research lab. She's a chemistry major, an honor student chemistry major now, and she was recently published her experiment on edible water capsules. So you can take sodium alginate and calcium lactate and make these water pods. I don't know if you've heard of the OHO. They used them in the London Marathon to replace water bottles. So there's one example, and there's many more, where I feel like introduction of chemistry as contributing positively to the world is going to inspire students to join the STEM fields. We want to prepare our students. I'm working on multiple ACS committees with industrial representatives, and they want students that are going to be able to come in and solve these grand challenges of sustainability. And even if students in our classes are never going to take another chemistry class again, I feel like them having knowledge of green chemistry helps them be informed citizens. Every semester, and this is just from this last fall, I ask in my 2311 organic chemistry laboratory course whether they value the inclusion, and you can see here over 75% of them agree or strongly agree that they value green chemistry in the class. That's pretty good. You always have the people down here. One or two people just can't be happy. All right, so here is my ending pay it forward. And that is I started with a snowball that took an experiment, and now we have lots of snow people all over the place. And this is how. Through my laboratory curriculum and undergraduate and graduate students, we've developed new curriculum materials that are feeding back into my laboratory curriculum. Graduate students, I personally don't have PhD students. They work for me in curriculum development, have developed new materials. Many of them I saw incorporate into their PhD research efforts. And most satisfying is these are just two examples of my former TAs. They're actually both head TAs that are now professors at other universities, contributing green chemistry curriculum materials and teaching it. So new students, new professors, new students carrying on green chemistry. On the opposite side, feeding back into the laboratory. So the opposite side here, as I said, I had undergraduate students that want to learn more, took the green chemistry course, or developing experiments, becoming high school teachers. I probably have 8 high school teachers out there that I'm pretty convinced are doing some green chemistry or going on to graduate school, and they're feeding back in their students come to the University of Minnesota to learn more. So lastly, I'd like to acknowledge, I couldn't possibly acknowledge all my students with the experiments that I gave a survey of, but as you can see, a mixture of undergraduates, graduates. I've had some green chemistry postdocs with me and work with me, and high school teachers also. Faculty collaborators have been awesome in allowing me to translate their work into new curriculum experiments, so I appreciate their collaborations. And here are my funding sources. The Minnesota Pollution Control Agency started me out with a grant for curriculum design. The NSF Center for Sustainable Polymers, we're in our 11th or 12th year, and I'm so proud to be a part of that center. And then I collaborate with an Augsburg professor, Michael Wenzel, and he had some funding that has helped us design some of these experiments. So finally, thank you for your attention. I'll be happy to answer any questions. My final note is I'm a huge Lord of the Rings fan, and I'm quite convinced, as Gandalf said, all we have to do is decide what to do with the time that's given to us. I'm quite convinced that Gandalf would be passionate about green and sustainable chemistry also. So thank you for your attention. Are there any questions?
Okay, Jane, thank you very much. I'm sure that Dr. Wissinger would be happy to take questions from the audience. If you joined late for any reason, please type your questions into the Q&A box here in Teams. There's already some come in, so I will read them out. And Dr. Wissinger, I did not know you were a huge Lord of the Rings fan, but I am also, so we'll have to geek out on that at some point.
I could probably give every single lecture, I could make some association to a Lord of the Rings.
Me too, actually, me
Yeah.
too. So maybe we'll have to have like some sort of virtual Lord of the Rings war or something at some.
That's right.
Okay, so from the audience, let me go back to the beginning of the question. So one person asks, how long would you estimate it would take for plant-based plastics to replace petroleum-based plastics? And what is the difference in cost in being able to produce the plant-based plastics?
So there's plant-based plastics right now, the PLA, that are competitive on the market. They're out there. I could hold some up here. I have them by my desk. The problem is they are, for example, the PLA cups, of course you guys can't see this, they will melt under hot temperatures. So there are plant-based products out there. The University of Minnesota uses them in all their dining facilities. You can find them in grocery stores, but they, especially sports arenas that have the compostable plastic, those are all compostable. Now what that means is you have to take it to an industrial composting facility, but it will degrade in 3 months versus 400 or 500 years of a PET product. So it's out there, it's on the market, and it's competitive. So I've purchased it, you know, it's right now pennies more. If I had my graduation parties for my children, then I purchased the plant-based plastics. So but functionality is the challenge. You know, we can pretty much make a plastic to do anything. A diaper with, you know, hydrogels, or a car bumper, or something soft and flexible. So the challenge is to be able to create all that type of functionality with these plant-based plastics.
Okay, great. So
does that answer the question?
yeah, hopefully we'll see. We have a whole slew of questions, so we'll move right on. I think that was it seemed like an excellent answer to me. And hopefully we'll get Seton Hall to use plant-based plastics at some point on campus. That would be excellent.
We even have the containers where everybody can put these now for industrial composting. And Target Field is totally the Twin
Yeah,
State.
I remember. I think the University of Washington has that also. I spent a fair amount of time there, and they've been using compostable plastics for quite some time. The next question is, how can we remove microplastics from the environment? Do you have any insight on that, or what can be done with or about microplastics?
First of all, we're at the stage of just identifying microplastics, and there's a lot of great studies out that are showing where they are and where they're coming from. The large majority are coming from our clothes. Washing our clothes is producing a lot of microplastics. So a recent study by the University of Minnesota shows that there is, I'm sure you know this, microplastics in our beer, in our salt, in tap water. It's not clear whether it's harmful to us ingestion yet. That verdict is still out, but getting rid of it, there is not good. You know, they're using some nanomaterials, or the question is, the ocean is the biggest challenge, right? There's microplastics in the fish we're eating. And there is not a clear solution at this point. It depends on what you're trying to remove it from. Water, soil, consumer products. cosmetics.
So maybe one of the best places to start is to change the sources of the microplastics so that we don't keep making them, right?
Yeah.
Okay, so the next question is, can the Triblock polymer be used, could it be used to make tea bags to improve health? And then the questioner also says, thank you so much for your excellent interdisciplinary talk.
Thank you. Those particular Triblocks are too expensive for commercial products. There's also one from the center that is based on menthol. So that would be an interesting application, but it's not competitive cost-wise yet. Now, the Center for Sustainable Polymers has started a new company, and they are working on making a Triblock polymer product that is going to be economical, we hope, in the future. It's petroleum is just so cheap, especially today.
Especially today, literally
yeah,
today, right?
I know. Yeah. So it is hard to compete with that. And so what's going to drive it? We consumers are going to drive it. Are you going to be willing to pay more?
Right.
What would Gandalf do?
Right. Okay, so Dr. Marzabadi asks, does your organic lecture course incorporate green chemistry in parallel with your lab sequence? And if so, what text are you using?
That is a good question, and there is no great textbook out there. The Cardi book has the most in. We're using Carey, which no one's really happy with, but it has some green chemistry in. Basically, the instructors, and I just did a survey of the whole department not too long ago, and I didn't show that data today, all of them, when they teach oxidation, they do teach greener oxidations. So it's selective with the type of chemistry in the lecture courses. So there's nuggets, I would say. Would I like more than nuggets? Yes. But
yeah, I think that's what Dr. Marzabadi and I have discussed also, simply in looking around. So we need to, that's why I think I said at the Beyond Benign meeting, we need to get together and write one, right?
Yeah, I mean, Alexi from North Dakota State just published a review of the green chemistry content in all organic textbook, and it's dismal.
Yeah.
It's dismal, pretty much.
Yeah. Because even the Cardi book doesn't really have very much.
So. No.
So the next question is very similar to the recent question. Basically says, I think this is more or less answered, but how do we overcome the challenge of decreasing oil prices, making petroleum-based polymers cheaper? It seems like this is working against the green polymer movement. So maybe instead of comparing costs, maybe I can rephrase that question slightly and ask you what you think. How do we make, aside from just hoping that people will invest in the planet by paying more money for a more expensive polymer, what do you think the other hooks are to get people interested in greener polymers?
Yeah. Well, the Center for Sustainable Polymers is really focused on, the multi-prong approach. It's going to have to be used. So there are things you can add to our current polymers that makes them more degradable, and instead of calling it end of life, we want end of use for a particular polymer, that it can be, remade into something else. We could never make another polymer plastic again anywhere in the world, and we have enough of this material. There's too much, but that's not going to happen. And the current recycling is not working either. So we need to find ways to repurpose a lot of the polymeric materials that we have. And right. People have to buy in.
Right.
Why isn't PLA, why is not compostable these PLA products made from corn everywhere?
Right. I think inertia and people who, you're just used to things one way, or
Yeah.
cheapest, or you've been doing it that way for 20 years or whatever it is. Yeah. So
there is a good book I would recommend called Plastics, A Toxic Love Story.
yeah.
And it's really interesting because it shows how the polymer companies had to really push and push and push to have people give up their paper bags. And now we're trying to go the other way. Not that it's not a complicated issue there, but yeah.
Okay, so somebody is asking if Minnesota does on-campus teacher training. Do they give summer courses to teachers, high school teachers, or anything like that?
They do, yes.
Mm-hmm. Okay.
Maybe not this summer.
Right.
Yeah.
And then also, I don't know if you have anything to say about this, but do you have any insight at all into what you think might replace rare earth elements in their various uses? Cell phones are mentioned here, but of course we know that wind turbines also require them. Does that ever come up in your work?
Not, I mean, I've definitely heard talks where people are trying to replace some of them with earth abundant metals. Iron's out there a lot and being explored. So I know there's lots of research in the area.
Yeah.
But
okay, it looks like we have maybe just one more question, and that is, so do the plant-based products biodegrade when they're buried in a landfill?
they do not. They need oxygen and they need microbes. And a landfill is like the worst place for anything to degrade. There's nothing there. And I'm sure people have heard that they've now found microbes that will degrade PET, but it needs to be in the right environment. So our habits of landfilling everything are not sustainable.
All right, so, let's see. Wait, there is one more question. I can't tell quite what the question is, but it's talking about a green chem textbook. I don't really know what the question is, unfortunately, the way it's worded, but I think the idea is that it would be attractive to students if one existed.
I mean, there are some out there. What one finds when you try to teach a dedicated green chemistry lecture is there's so many different topics to cover that most people like to choose the ones that they feel are going to engage the students the most. So,
Right.
And now I have my green chemistry notes with the title of chapter 1 and chapter 2, but that's as far as I've gotten. There's just so much to explore and so many connections.
So the questions keep rolling in, and I don't know when I'm supposed to cut off, so I'm not going to cut off. I'm just going to ask you, I guess, the last question now. We'll make this the last question since you've been so generous with your time. Do the physical properties of plastics directly affect their degradability? If we use plant-based plastics to make and are able to make hard, sturdy, high heat stability plastics, would that reduce their degradation rate significantly?
It's definitely a balance. What they're looking at is trying to incorporate functional groups. For example, an acetal functional group might be more degradable, but it's not just about whether it comes from plant-based, really, because if the polymer's not permeable, I mean, there's lots of, or if it's cross-linked, there's lots of dimensions that need to be explored. But there's science going on to engineer organisms particular to certain types of plastic, and certainly that engineering, I believe, is easier when you start with a plant-based source. So a carbohydrate, for example, or a recent publication from the University of Minnesota uses a polymer based on salicylic acid, aspirin structure, salicylic acid. So I hope that will make a good green chemistry curriculum experiment. But because it is plant-based, I would say in that case, they are finding it's degradable. So that's really exciting. So in some cases, the answer is yes. Let's do it.
Okay. Just because I think it's an interesting question, I am going to ask one more, and then this really will be it. Do you believe manufacturers should take responsibility for the disposal or repurposing of packaging materials?
Ooh. It's like, should companies be carbon taxed?
Right.
Along those lines.
It's a complex question.
It is complex because, a company may produce the pellets that go to the company that makes the product. So who should be responsible? The person who made the polymer pellets or the person that converted it into a polymer product that may have changed, combined other things with it to make it a little different for whatever purpose it is. So it's a complex question.
Right.
But that's a really good question.
Okay, so with that, I am going to first of all tell you that I'm sure if we were all together in person, there would be thunderous applause at this point for the outstanding talk you have given us. Really, really appreciate you doing this, Dr. Wissinger. And second of all, I would be certain that many listeners would come up to want to talk to you in person. And so I want to say again how regretful I am that you can't join us for our poster session this evening, meet all of the students personally, but we are hoping that you will come and visit us in the fall if that's viable, or next spring. We'll see what works the best. But we are determined to invite you to our campus so that you can meet not only our amazing students, but the other excellent faculty, as well as our administrators, all of whom I think, from hearing me talk previously, the sustainability and stewardship are at the very heart of the mission of Seton Hall University. So this is very important to us. So we, again, as I said at the beginning, we're honored to have had you join us. To the students who are out there, I would tell you that Dr. Wissinger has an email address and she's easily findable at the University of Minnesota. So if you have more questions, please go ahead and follow up with her that way. If you would like to have her come to campus as much as I would, please tell your advisors that so that we can make sure that happens soon. And with that, thank you again. And we will see you on campus sometime soon, I'm sure.
Thanks, David. Thanks, everybody, for joining us. It was fun.